it full screen. Let's start the session 8. So we know there are different, we characterize nanomaterials depending upon the dimensions, like 0D, 1D, 2D, and 3D. So again, we define the definition of 0 dimension, 1 dimension, 2, and so on. These dimension nanomaterials as the dimension which is not in the nanoscale, that defines the number, define the D. So if I take 0 dimension, then all other dimensions are not in nanoscale. So there are like quantum dots and other types, fullerenes, etc. And if I go on 1 dimension, I have rods, wires, etc. In 2 dimension, we have thin films, and 3 dimension basically it's a bulk material, but it has the characteristics of nanomaterials. Like for example, if I have bulk material, like if I have bulk rod, which has all dimensions like mm in micrometer square or in millimeter, then the grains which the material is made up of is in nanoscale. Then we call it as 3-dimensional nanomaterials. Another example is, for example, if I have a bulk material and in that material we have precipitates of nano size, then again not so 3-dimensional nanomaterial. So those are it. And after that, sir has discussed like different types of process from which you can synthesize the nanomaterials. And I will be go on like, so I will be following this order like 0D, 1D, 2D, 3D. So in the ascending order. So in previous class I have discussed up to like two-dimensional synthesis, 2-dimensional nanomaterial synthesis. So I will just again briefly recap what I have said before. So the first one is inert gas condensation process. So this one is the first process that I mentioned here is inert gas condensation process. So let me write it. This is inert gas condensation. And same process, but the name will get different. Here it is inert gas expansion. So the first process is inert gas condensation process, and is the same. We have a heater, we vaporize the material, and the material gets cooled, and there is the material gets cooled on a surface, and that is called as a cold finger, and then we collect in the bottom of the tray. So what we normally do is we take an inorganic material, vaporize in the presence of vacuum chamber, and we pump the inert gas, which will act as a ship. It will take these molecules to the top, and it makes it to condense, and we have nanoparticles. So in this process, during the evaporation and traveling and condensing, we have this clustering process. So the nanoparticles get clustered, and we know nanoparticles are high surface energy, so they try to cluster. They try to form clusters, right? They have 2-3 nanoparticles, and they start to do the clustering. Like this is a nanomaterial and this is a nanomaterial. They try to come too close together and form a cluster. So if we can control the process parameters, we can control the clustering, but not to the high extent. So this is one of the drawback in inert gas condensation. And the next process is the inert gas expansion. It is same as the inert gas evaporation, where we have a boat, we heat it, and we have inert gas which acts as a ship, which takes this vapor to colder region. So they condense, and then again we have a clusters, we form nanoparticles, right? So these two processes are same, but the only difference is one is we have an expansion. During expansion, we have less clustering when compared to inert gas condensation. So this process is used. And the next we have a sonochemical process, right? We have a sonochemical process. We have two terms, one is sono, one is chemical. Sono is nothing but the sound waves, and chemical is not the chemical reaction. So, and because of sound waves, we have a chemical reaction. Now, how just the sound waves can create a chemical reaction? We have an ultrasonic horn which use sonic, uh, which use ultrasonic like sound waves into any medium, and this medium has a, if we have if I take an electric field have a positive and negative electric fields, and if I take a wave, it has a crest and trough, and if I take an alternating electric field, it has a plus positive E value, and it has a negative E value. And if we go on doing the same for the sound waves, then we have a positive pressure region, we have a negative pressure region. So the same thing is happening, and during this process we have formation of bubbles, and these bubbles start to coalesce, and once they reach a critical size, they rupture, and during the rupture we have a huge production of heat, which can make a chemical reaction possible. So from this we can generate like 2 nanometer size, and large volume of nanoparticles can be made. Now the next is sol gel process. This again is for making zero-dimensional nanomaterials. So sol gel we have a solution of precursor, mainly metal alkoxides, and subject to polymerization to form a sol. And sol is a discrete finely dispersed particles, and this suspension is converted to gel by some chemical treatments, like adding some surfactants. And this enormous molecule, once we have polymerization and we have this enormous molecule, and this network is called as gel, and if we evaporate the solvent from this gel, will give a nanoporous membrane. And if we just stop at the sol process without doing the gelation process, if we just stop at the sol process, and when we do the precipitation, we have this discrete nanoparticles. See, we are producing two types of materials. One is a zero-dimensional nanoparticles, and another is a two-dimensional, three-dimensional nanoparticles, depending upon the nanoporous, the thickness of the nanoporous membrane, right? So, and the final for production, and the final process that you have discussed, one was the molecular self-assembly, and where molecules are self-assembled, and another was 2D nanofilm formation, which we called as a Langmuir-Blodgett technique. Let me write it. Langmuir-Blodgett technique, right? Yeah. So we have fatty acids. In fatty acids, we have one is hydrophobic and hydrophilic ends. So those with the hydrophilic ends will get attracted to the substrate, and this substrate once was taken out from the medium, so we have a monolayer of fatty acids attached to the surface. And the next process is the electrodeposition process. In the electrodeposition process, we deposit nanofilms on our electrodes or substrate, and the main process that we follow to form nanofilms instead of what we call the dendrites in the structure. So how to produce nanofilms instead of columnar grains during, like, when we are transforming one phase to another phase during solidification, we have dendrites or columnar grains. And for example, if you are talking about a pure metal, we have a thermal dendrites. And if we are talking about alloys, we have a constitutional cooling. And because of constitutional cooling, we have a constitutional normal dendrites, or we call as in normal convention we just call it as dendrites. And if you are talking about pure metals, we call it as a thermal dendrites. So to avoid this columnar formation, what we do, we have a pulse current, like the voltage the voltage rises and drops, and we, for example, if you are applying 5 volts, so we start at 0 seconds and we give 5 volts for 3 seconds, and we have a voltage pulse, and then again we drop it to 0, and we again give a dwell time for like 10 seconds. So we create a pulse of voltage, so that we created nucleation sites, not the growth process. One should remember. During this process, we provide pulse to have nucleation sites. More number of nucleation sites, less growth process. So more is nucleation, formation of nucleation sites, so more the grains will form. We have more number of nanocrystalline grains in thin nanofilm. If you are forming bulk films, like for example micrometers, then we have a nanocrystalline grains. So now finally came to PVD. This is a physical vapor deposition process, and this was a chemical vapor deposition process. And here what we follow, we want to form a 1D or 2-dimensional nanomaterials. Right? In chemical vapor deposition process, we have a substrate. For example, if I take like copper or silver substrate, and we purge carbon monoxide gas above this, and we maintain the temperature below the gasification reaction. Right? We have this reaction for 2CO gives rise to C plus O2. So the forward reaction, the reverse reaction is a gasification reaction. So if we maintain the temperature so that we have a reverse gasification reaction, then we have the formation of a carbon. So the carbon will start depositing onto the copper or silver substrate, and the copper starts to diffuse into the copper substrate. Once the copper reaches saturation limit, and the copper again tries to precipitate out from the copper. So during this precipitation, we have the formation of the one-dimensional nanomaterials like CNTs. And depending upon the type of substrate and the shape of substrate and the temperature, we can have single-walled nanotubes and multi-walled CNTs. And same goes for the physical vapor deposition. In physical vapor deposition, we just apply raw heat, and the heating can be provided through the heating can be provided through just heating in presence of furnace, or putting a sample in a furnace, or we can do the sputtering, and we can even do the laser ablation process where we intensify the heating zone, only one spot. So this process is physical vapor deposition. And chemical vapor deposition, we do the heating part, but the main driving force here is a chemical reaction to form a specific compound. So that is the difference between the PVD and CVD. Let's move on to two-dimension, or for example, if we take making of a three-dimensional nanoparticles. So far we have for until now we have two-dimensional nanoparticles, and from now we will be discussing on the synthesis of three-dimensional nanoparticles. So there are two ways we broadly synthesize the synthesis of three-dimensional nanoparticles in two parts. One is a top-down approach, and another is a bottom-up approach, and there is an intermediate process. So in the top-down approach, we have a bulk material, and we go on from the macro size to the nano scale, And basically we are not reducing the whole dimension of the material, but the characteristics of the material, like the grain or the precipitates that have that are, that are the part of the system. We are making them to be in the nano range, and the bottom up approach, we are starting from scale less than a nanoscale, like unit gas condensation, soldier, and self assembly, where the treatment starts from a molecular range. So the first process is melt spinning. In melt spinning, we have a reservoir of molten metal. We have a turn dish, and in turn dish we have molten metal, and from that turn dish is attached to a screw. Screw is nothing but a passway from which the molten metal passes, and that molten metal is sprayed, diffused onto a drum, a rotating drum, which moves at a very high rotational speeds, like omega, which is the rotational velocity. Of omega is the 1000 RPM. 1000 RPM at low temperatures, like maintaining the temperature of minus 140 to 180. So these temperatures can be achieved with liquid nitrogen. So we have the formation of ribbons in this process. So to decrease the time required for the transformation from solid to liquid, and the time, the rate of undercooling will go up to the power of 6 kelvins per second, depending upon the type of coolant we are using. And a jet of liquid melt is squirted down to the spinning water cooled drum. So the final result will be the nano ribbons, example laminated transformer core, or we can even get the glassy structures. So this is one of the process for the production of nanomaterials, and the other one is the laser surface melting. So in this laser surface melting, we use laser beam for rapid and focused melting. The substrate act as a heat source, right? Because of the fine spot, like we have a 10 micrometers. For example, if you take 10 micrometer laser spot, and we are focusing on to focus onto a certain space, we have an intensified heating zone at that position. And besides that, we have a whole material, right? So the other part of the material will act as a heat quench, so which conducts heat away from the intensifiers. So the substrate act as a heat quench, creates an amorphous or nanocrystalline structures. Example, this process is used mostly to form the amorphous silicon for cheap solar cells. So this process is very crude and not used in this process is very crude and not used in the formation of the chips used in course. But if you want to make solar cells at a low price, then the laser surface melting can be used to make the proper laminations onto the screen. And the next one is the next process is the foil beating process. So it's an old process to create very thin structures. So we heavily deform material using a hammer. So this process is mostly used to create gold foils or gold wafers, and this process is even used to get a silver, very thin silver layer. So I'll discuss. First, this is a top-down approach where we have a material of more than in all three three dimensions have millimeter range, but after heavily deforming into one direction, the grains will deform into certain direction, which results in elongation along one axis, which results in the formation of nanocrystalline grains. And this process is a melt spinning process. As I mentioned before, we have a liquid melt which is put onto the cool, high-speed cool rotating drum, which forms the nano ribbons, and we have a laser surface hardening process. The other one is the ball milling process, where we have a this is a top-down approach again. So this is a bottom-up approach, and we have a material, and material gets heavily deformed to form, for example, we have a grain, and the powder particles will have different grains in it. So once we start heavily deforming, this grain will turn out into a nanocrystalline grain. And why nanocrystalline grain? Because the formation of the defects, and these defects will try to form a strain-free grain, which is called as a decrystallization. So we have the formation of a nanocrystalline grain. And the other process is the micromachining, where again the material is heavily deformed to give chips or different types of deformed shapes. For example, to create feature on surface. So depending upon the type of machining process, the different types of collected spark will be taken into account. And the other process, which is the bottom-up process, which is called as a pressurized sintering, where if we have powder particles, which are in particles at nanoscale, and we try to consolidate and form a compact, and this compact has a nanocrystalline structure. So it has the grains in nanometer. This is another sintering process, and these two processes are called as nanoprofiling. What we do is we have a material, and we focus a very fine beam of either it is an electron beam, or it is a plasma, or the laser beam, to locally melt the surface and again recrystallize it, so that we have a nanocrystalline grains there. And again, we are talking about three-dimensional nanomaterials, where the whole material is not in nanodecimal, but the characteristics of that material are in nanoscale. Another was the other process, the lithography. And there are different types of sintering process. In this process, we are just forming. If we avoid this heated dyes, then we are just forming green compact. And we heat it. We have a diffusion process taking place, and there is a phase transformation again taking place. So we have a different compact consolidated product, and here we have another profile. And in our profiling process, we have a bulk material. For example, it is in 1 mm by 1 mm. What we are trying to do is we are focusing our spot at a certain point. For example, I want to focus onto this area. So this area gets melted because of localized heating. during the transformation. I have mentioned before, for example, if a solid is turning into liquid and we have a G curve, G versus temperature curve. Right? So let me add a slide. Solid is transforming or liquid, let's say, for simple case. Let's say a liquid is transforming into solid, and we have free energy versus temperature diagrams. And for liquid we have one, and for solid T equals to Tm. Here we have free energies of both liquid and solid or liquid, and undercooling defines the driving force for solidification. So if I write GL equals to HL minus T SL, G is the free energy of liquid, H is the enthalpy of a liquid, S is entropy of a liquid, and G of solid equals to enthalpy of a solid minus P enthalpy of a liquid. So this is 1, this is 2, 1. If I do 2 minus 1, then Gs minus ZL equals to HL minus HS minus HL minus T this will come to minus 1 S, so minus into minus plus, so this is minus S. So delta G equals to delta S minus T delta S. So T equals to Tm. We have Gs equals to GL. This will turn out to be 0. Then delta H minus delta H equals to Tm delta S. So if we try to substitute in equation number 3, let's say for temperatures near to operating temperatures, the H and S are independent of temperature, or H and S doesn't change much with temperature. So like dou H by dou T is very small value. T delta S will be delta H by T. Tm minus T Tm into H. So final relation will be delta G is directly proportional to delta T, and this delta T is our undercooling. So the more is undercooling, the more is the driving force for the formation, and this in turn will increase the nucleation rate. Right? So the less is the temperature, the higher is the nucleation rate, and there won't be growth, or there is not much chance for the growth process. Why? Because the diffusion, right? The diffusion equation 2. From previous slide we know the nucleation rate will increase with temperature, with decreasing the temperature. So here I can decide if I denote the nucleation rate as I. If I denote my nucleation rate as I, then it depends on the undercooling. The higher is the undercooling, the higher will be the nucleation rate. But what about the diffusion? Let's write derive the equation how the diffusion will depend upon the temperature. Suppose if I have two surfaces, right, which are separated by some distance, A. So atoms are jumping from 1 to 2, and there are also atoms are jumping from 2 to 1. So then J1, the flux moving from 1 to 2 will be from 1 to 2. So now let's suppose we have an atom here. It is jumping from 1 to 2. It has the degrees of freedom of 3 in all 3 directions, and also we have negative directions, right? So there are what the degrees of freedom of in a single atom in a space is 6. So what is the probability in going in any direction will be 1 by 6 times what is the concentration, 1, that would be N, the number of atoms per unit area, times number of atoms times tau. What is tau? Tau is the time constant, the amount of time taken by an atom for a random jump, or you can call it as a frequency. Frequency. Now the units are matched. So J is flux, which is the number of moles. If you're talking in terms of moles, then moles per unit area per second. And if you're talking in terms of numbers, then number of atoms per unit area per second. Right. So this is for J1 to 2. Now what is for J2 to 1? It will be 1 by 6 into times frequency. Now the net flux J net will be, if you assume the atoms are more number of atoms are jumping from 1 to 2 than 2 to 1, then J12 minus J21, 1 by 6 times frequency and 1 minus N2. So N is the number of atoms per unit area, and if we try to convert it into the volume rather than area, then N1 will be A times C1 minus C2. Let's say at 1 we have a concentration C1, and at 2 we have a concentration of C2. Then sorry, this is not N1 is equal to C1 minus C2, it's just AC1, and N2 equals to AC2. Right? Then N1 minus L2 is equal to A of C1 minus C2. So let's substitute 1 by 6 frequency A and C1 minus C2. So if you assume we have a concentration, there is no assumption. For example, the C depends on X, right? So the concentration changes with respect to the distance. If the concentration doesn't change, then then that problem is a constant concentration problem. Well, uh, that that means the system has attained equilibrium, and system doesn't need to migrate the atoms from one place to another place, and the diffusion happens because of the mainly because of the concentration gradient. Again, that is again a crude way to define the diffusion, but mainly the diffusion happens because of the gradient in chemical potential of the atoms, and the chemical potential can be different things. For example, if we have a potential gradient because of a species, the amount of species, then we have a chemical potential. If it is because of the pressure, then we have a pressure gradient, and again we can have a pressure potential. If we have a charge, then we have again the charge potential. If we have a magnetic field, we have a magnetic field potential. And if we are talking about the activity, then again getting back the chemical potential. So the diffusion mainly depends upon the gradient in chemical potential, not only on concentration gradient. Because if we only talk about the concentration gradient, the concentration gradient term can verify the downhill diffusion. Where, for example, if we have at one surface we have a higher concentration, another we have a low concentration, then the atoms will travel from 1 to 2. This is normally called as a downhill diffusion. And what happens if we have a G versus X plot? What happens now? If we have a alloy composition at here and we give enough temperature, then this alloy will decrease its gift free energy. And here we have a uphill potential where the atoms are getting richer and richer in one phase. So for conventional purpose, we are using the diffusion only depends upon the concentration gradient. So if C1 and C2 are the concentrations and 1 and 2, and let's write if we define in terms of a Taylor expansion, then C2 will be C1 plus, let's write it more mathematically, C2 of X, C1 of X plus dou C by X. We know that del X goes to A. So net flux will be 1 by 6 times frequency times A, which is C1 minus C2. C1 of X minus dou C by dou X del X. Del X is A. Systems cancel. We have 1 by 6. We have frequency times A square dou C by X. This term this D is called diffusivity, and the diffusivity has a relation 1 by 6 frequency times A square. Now again, this frequency we normally call it as a jump frequency, and how this jump frequency depends. It depends upon the type of atoms, right? Not type of atoms, but where the atoms are positioned in the crystal structure. If you're talking about the voids, then this jump frequency will be very high. And if you're talking about the substitution atoms, then this jump frequency will be orders less when compared to the interstitial atoms. And the reason is simple: the interstitial atoms will have more space to roam around when compared to the substitution atoms. But substitution atoms mainly depend for the substitution atoms to have a different diffusion. It only depends upon the frequency concentration, so not the frequency, the vacancy concentration. The more is the vacancy concentration, the higher will be the diffusion of substitution atoms. So this frequency, this jump frequency will again depends upon the atomic frequency times exponential minus delta G by kT. So again it depends upon the temperature. So higher will be the temperature, the higher is this jump frequency. So first we define our nucleation rate, then we have our growth rate. To have a minimum growth rate, we need to have diffusion. So for higher nucleation rate, we need to have proper undercooling. So for more nucleation, we need to have a high undercooling. That means the final temperature is very much less than initial temperature, right? So we need to cool the system. But what about the growth rate? The growth rate depends upon the diffusion. The diffusion again is inversely proportional to, is directly proportional to the temperature. So higher is the temperature, higher is the diffusion. TF should be near or equals to Pi. Then we have a higher diffusion. So these both are contradicting to each other. So to maintain a perfect balance, we have like this. So at this temperature, we have both higher nucleation rates and higher growth rate. But this is my growth rate, this is my nucleation. So higher nucleation rate will be obtained at lower temperatures, higher growth will be obtained at higher temperatures or near to the melting points. So higher will be the undercooling. More is nucleation. And that is the reason why we have nanocrystalline grains. Crystalline grains. Why? Because we are not giving enough time, or not even, again, the diffusion will again depends upon time and temperature. So we are not giving enough temperature for the diffusion of atoms. So that's why this process will come into the three-dimensional nanomaterials, where we have a bulk nanomaterial, we have a bulk material, and because of the localized heating, we have a melting and sudden quenching of that region, results in the formation of burst of nucleation sites. And so the burst of nuclei, which results in formation of nanocrystalline grains. Because of a lower temperature, there is no diffusion, and because of less diffusion, we have less growth of grains. So we have nano characteristics embedded in a large material. So this process, the nanoprofiling, comes under the three-dimensional nanomaterial. other process is the lithography process. So lithography process is mostly used in the semiconductor industry. So let's first discuss about photolithography. First, we want to have a design. When we think about the silicon wafers, which were used in semiconductor industries, and they have very small integrated chips, right? There are many transistors in a 1 mm chip. There are like lakhs, there are thousands of transistors, and this amount of transistors is going on increasing with the time. So to define or to make a transistor of that small, we need to create a certain structure. So to do that, we use a photolithography process. At first, we have a silicon wafer on which we deposit or we form a silica layer. It is nothing but the oxidation of silicon. We will form a silicon layer, and then we apply the photoresist. And depending upon the type of lithography, like positive photoresist or negative photoresist, the process remains same, but the thing that changes is with respect to the mask. So mask has a certain shape where it allows light, and certain spots it act as an opaque medium. So at first we have a silicon wafer, then we have a silica point, and then we have photoresist. So and then after that we apply a mask. And after applying mask, we columnate with the ultraviolet beam, and this ultraviolet beam will be allowed by some portions of mask and stop by the opaque portion of mask. And if you have a positive photoresist, sorry, if you have a negative photoresist, then this UV beam will make the surfaces which are not exposed to the UV region will remain the same, but the regions which are exposed to UV beam will have a different characteristic properties. After that, we dissolve the exposed resist, and then we do the etching to remove the silica layer, and the concentration of etchants that are to be taken should be maintained, because if we have a very high corrosive etchants, they can eat away the surfaces, the unwanted surfaces. Right? For example, some etchants will just dissolve even after remain in some corner places and dissolve more there. So we need to avoid those process, and then we do the etching followed by the removing of a remind resist. Then finally we do the etch underlying silicon. So as a final process, we have a definite structure or a definite profiling on our silicon wafer. And there are other processes like soft lithography process, where we have a soft PDMS template, and it has again certain profiling on its surface, and we apply ink to it. And the other part where we are going to apply is we have a silicon wafer, and then we have a gold layer, which is mainly coated or any thin film that is deposited. And then what we do is then we press this inked PDMS template with a silicon layer containing the gold layer, and finally we have a printed surface. In the other process, we have a polymer linked template. We have, instead of the gold layer, we have a liquid polymer, and after solidifying, we again have a definite profiling, not with a solid gold layer, but with a solid polymer. So this is about the soft lithography process. So this is the final summary of different processes that have been discussed to make the nanomaterials of a different scale. So Let's just give a recap. We have an inert gas condensation. We just condense, we first evaporate and then condense. This is again the bottom of approach where the vapor molecules are getting condensed forming clusters. Right? Either we have a free jet expansion or inert gas expansion, and it's the same process of inert gas condensation where the final part gets changed. At first we have a condensation, but in the second we have an expansion to avoid the clustering. And the third is the sonochemical. By using the sound waves we create cavities, and these cavities will grow in size, and once they reach a specified size they rupture and releases enough amount of heat to run a chemical reaction. And if the chemical reaction is self-sustainable, then or exothermic chemical reaction, then once we turn off the sound, the chemical reaction will continue. And the fourth is the Solzer process, where we create a discrete, if we just stop at solve process, we have a discrete nanoparticles. We do the gelation and then we dry it or remove the solvent from it. We have a compact compact nanomaterial, which it has a characteristic of nanoparticles. And the fourth one is a molecular self-assembly. In molecular self-assembly, we have molecules which self-assemble to a substrate. For example, if I have fatty acids, it has a hydrophilic and hydrophobic end, just like micelles used in surfactants. The hydrophilic end will get attracted to the substrate, and the hydrophobic end will remain facing towards the solvent. So we have a thin layer formation. Suppose this is my substrate, and I have a thin layer formation. Suppose substrate, these fatty acids will form a monolayer, a molecule thick film. And when it coming to wires and tubes, again we have a molecular self-assembly process to form this, and we have a CVD process, just like I mentioned before. And depending upon the chemical reaction we are doing in the system or on the substrate. For example, this is my substrate. Suppose this is my substrate, and I have an environment like this. Suppose again if we take a carbon monoxide, right? So if I have a carbon monoxide, and suppose let's say if I burn coke in the presence of oxygen, C plus O2 plus H2. This is gasification reaction. We need to maintain the temperature like below the equilibrium temperature. Then this reaction will follow backwards, and this 2CO will dissociate into the carbon and oxygen. So if we have a substrate here, for example, if I take copper or silver, so and due to less temperature, the carbon monoxide, due to less temperature, the reverse gasification will happen. So the carbon will form a layer on the top of the substrate, and because of the temperature, this carbon will diffuse. So if you maintain the temperatures above 600 or 650, this carbon will diffuse into the copper or silver substrates, and once the substrate reaches the supersaturation stage, the splitting of the solid will happen. The splitting of solid atoms will happen. So the carbon will so uh, the carbon will form nanofilms. So sorry, not the nanofilms, but CNTs. So let's say this is my substrate, and I have this is my substrate. Once it reaches certain the supersaturation range, and it spits out the solute, and this solute will form the CNTs. And depending upon the temperature, the type of substrate we are using, we can have single wall nanotubes, carbon nanotubes, multi-walled carbon nanotubes. So this was that type of process, and again we have an arc discharge. The process is the arc discharge process, again the same, to form the wires and tubes, and to form films we have a number of processes. We first start with the lithography process, and then we have a micro machining process where we have a nanoribbons, right, where we have a shear deformation. So we have a machining formation of this ribbons type, the shapes, ribbons, and depending upon the shapes, there are different types of material that will be exposed. So we have a micro machining process, and then we have patterning, and depending upon the patterning, like to form the profiling, we have focused ion beam and electron. In focused ion beam we have a sputtering of atoms, like we sputter the atoms from the surface. For example, if I take if I have a gallium pool, and on the gallium melt, and if I melt, if I apply the enough temperature or to melt an arc discharge at the surface, we have a gallium ions, and these gallium ions are accelerated to path and impinged onto a bombarded to a surface. Then we have a sputtering of atoms, where the atoms are removed from the surface. And again, then for thin film deposition, we have electrodeposition, we have sputtering and molecular beam epitaxy, and CVD, the chemical vapor deposition. Again, and the other process is a foil beating process. This is again very crude process, but the dimensional tolerance is very low. And other is the Langmuir-Brodgett process, which was used to create the monolayer fatty acids, as I discussed before above. And finally we have to form the bulk forms. Again, the material is not in 3 dimension, but its characteristics are nanodimension. So one is the equiangle extrusion, another is the compaction and sintering, because we have a powder particles which has size less falling into the nano regime. Then if we to compact it, these powder particles will consolidate and to form look like a nanocrystalline things. So that's how the compact and sintering process comes under the bulk form. So micro machining, electrodeposition, and sputtering can be done at the micro scale. These all processes comes under the nanoscale. Now that will be the end of the synthesis and processing. Now coming to the, so far we have discussed electrical properties, magnetic properties, and optical properties. So in optical properties we have seen the surface plasmon resonance. We have discussed in first few sessions what is surface plasmon resonance. We have 3 terms: surface plasmon resonance, right? So slide. When discussing about the optical properties, so we will be dealing with the mechanical properties now, but just recap what are the other properties we have discussed before. And when coming to optical properties, we have discussed the main point is the surface plasmon. So it has a three terms: surface, plasmon, and resonance. And this, the plasmon is nothing but the collective oscillation of electrons, and the plasma are dealing with the oscillations of electrons, and we have a surface. There are two types of plasmons: surface plasmons and bulk plasmons. And for simplicity, we are going to discuss about the surface. I'm going to tell about the surface plasmons. The surface plasma, for example, every material has a surface. So if we, for example, if we take about the nanoparticle, and it has its surface, depending upon the size, it has its surface, and we have a plasmon, the collective oscillation of electrons. So resonance, the two mediums are oscillating with the same frequency. Right? So the light, for example, the photon that we are going to introduce or impinge onto the surface of the nanoparticles is comparable with the collective oscillation of electrons. Then we have frequency emitted. Right? So, for example, depending upon the size, for example, if I have a 20, 40, 60 nanometer particle, and if I bombard with the same frequency of photon, then this frequency of photon gets with a different frequency of photon gets reflected. So, if, for example, if we bombard like white light onto that, which has a number of wavelengths, like 7 wavelengths combined in it. So, if we try to bombard with a nanoparticle, so each nanoparticle, depending upon the size, will give a different color. That is related to surface plasmon. And the other thing we discussed, like the electrical properties, right? Depending upon the size of the, for example, CNTs have very high thermal conductivity. Why? Because they have a dangling bond, one bond being unsatisfied. So those electrons are localized. Again, it has a high thermal conductivity. And also we discussed one was the electrical conductivity of optical properties, and also the the magnetic properties. They have a giant magnetic resistance, and depending upon the spin we apply. And yeah, so far those are the properties we have discussed. Now coming to the mechanical properties of the materials. So any material, if you want to use in certain conditions which undergo the stress and different types of stresses, like it can be the tensile stress or the compressive stress or the shear stress. So this stress strain relationships will give the study about the material, how it changes with respect to stress applied on it. Or the second one is the hardness, and the third one is the effect of temperature on the properties. And the fourth will be the fluid properties, and the fifth is the viscoelastic behavior of polymers. So we are going to discuss for now is the stress strain relationships and the hardness. These are the two things that we are going to discuss now. So let's start with stress strain relationships. Now, mechanical properties of a material determine its behavior when subjected to mechanical stresses. Right? These properties include, there are many properties that define the material when we are talking about the mechanical properties. Like depending upon the material, these properties include elastic modulus, ductility, hardness, and various measures of strength. So So when we are talking about the strength of the material in the basis of a stress strain diagram. So I will come to the stress strain diagram. Okay. So the stress strain curve is the basic relationship that describes the mechanical properties of the material for all three types. Like load here. So the all three types is nothing but the type of load, like the tensile, compressive, or shear. So starting with the mechanical properties. So these properties includes the elastic modulus, ductility, hardness, and various measures of strength. Mechanical properties are important in design because the function and performance of a product depends on its capacity to like resist deformation, or which if you want to have a material with high resilience, or you have more ductility, or if you want to have a material which is hard. Right. If you want to use the material in damping conditions, like to absorb the energy, use more harder material than the more ductile material, right? Because of higher is the ductility, the material will deform. And for example, if we are using some materials to take the force, like springs, right, to store the energy and again to give. So in design, the usual objective is for the product and its components to withstand these stresses without significant change in the geometry. That is one. This capability depends upon the properties such as the elastic modulus and yield strength. Let me define what is elastic modulus. So before that, let's explain what are the different types of static stresses which we apply to the material. There are three types of static stresses to which the materials can be subjected. One is a tensile, which is if suppose we have a material, we have an elongation or the stretching of the material, and the compressive, it will look like this, the compression, and another is shear, where the two forces are opposite to each other. This is the shear forces, and the stress strain curve is again I explained before. The stress strain curve is the basic relationship that describes the mechanical behavior of materials for all three types of stresses. Okay. Coming back to the material, this capability depends upon the properties such as elastic modulus and yield strength. So let's go to the elastic modulus. So what is elastic modulus? So let me come to this before. Suppose this part of the curve, this is the stress strain diagram for the conventional, let's say for the conventional metals. For some metal, this part will have a constant slope. So stress is directly proportional to strain. So if I remove the proportionality constant, and that will be equal to sigma times E times strain. So that is stress equals to Young's modulus times strain. So the slope in the elastic region, that is the Young's modulus. So higher is the Young's modulus, higher will be the slope. So to change, we need to apply more stress to have a little strain, right? Or the minimum strain. So if the elastic modulus is less, then we just need to apply less stress to have that to have that amount of strain. For example, if I want to have a strain of X, and if I have E1 and E2, so if I want to have a strain value of X, then which material should, suppose if I have E1 is greater than E2, so higher stress should be applied in the material 1 and the material 2 to have the same amount of strain. That defines the elastic modulus. Now again the yield strength or the yield point will be defined as the point where the plastic deformation starts or the plastic deformation begins. Okay. Here the stresses are that exceed the yield strength of the material must be applied to alter its state. In terms of the inelastic region, the shape of the material will be retained after the removing of the load. But in the plastic region, there is no retirement of the shape of the material, and if we need to apply stress to continuously deform the material or to change the shape of the material. So for that, the mechanical processes such as forming and machining succeed by developing forces that to deformation. Thus, there is the following: the mechanical properties that are desirable to the designer, such as the high strength, usually make the manufacturing of the product more difficult. It is helpful for the manufacturing engineer to design from the viewpoint, so that the material can be used for the following application. Now, again, going back to this, there are three types of static stresses to which the material can be subjected. We have tensile, compressive, and then shear. So here again, the stress strain curve, which we have discussed here, which gives a basic relationship that describes the mechanical properties of the materials for the all three types. Now, here we have three shapes of the material, and this type of material is used in tensile testing. So we have a gauge marks which tells me about the initial length of the material, right, before the deformation or before the testing. And this is my UTS, or ultimate testing machine. Why we use ultimate testing machine? Because we can perform both tensile testing and the compression testing. Now, tensile again. As I said before, there are three types of static stresses, right? One is a tensile stresses tend to stretch the material. Other is the compressive stresses tend to squeeze it. Shear remote stresses that tend to cause adjacent portion of the material to slide against each other, right? So here I am applying one force, here the opposite force. So it's like a sliding of the material of the top surface. For example, if I have imaginary line of the material, this is my top, this is my bottom, then there is a sliding of one surface onto another, which we call the shear stress. Now, the stress strain curve is the basic relationship that describes the mechanical properties for all three types. Right? Now, let's talk about the tensile properties. The tensile test is most common procedure for studying the stress strain relationship, particularly for metals. The stress strain curve is more particularly used to study the metal mechanical behavior. Right? In this test, this is our tensile testing machine. I have a gauge marks, which I said before, and if we are talking about, there are different types of shape samples we can use. The rectangular specimen or the cylindrical specimen. So if you're talking about the rectangular specimen, then it has a shape like this. It will have it looks like a dog bone shape. So if you have a rectangular specimen and these two parts are for holding, we again have a gauge marks, to measure the length. So if you have a rectangular specimen, then we have if you have a rectangular specimen, we have a rod shape. If you have a cylindrical specimen, we have a shape like this. And to avoid the discrepancy in the values, there is a standard to which we need to follow. For example, if you have a rectangular specimen, there is a certain width to height ratio, and if you are taking the cylindrical specimen, there is a specific radius to length ratio that should be maintained so that the values doesn't change. For example, if I do experiment in some place, and if I do the experiment in some other place, and if I take the different sizes, there will be difference in values. So some societies has declared a standards to follow. So in this test, in this test, the force is applied. For example, in this test, the force is applied that proves the material. So at first, the material passes through the elastic region. The material passes through. It tends to elongate and reduce its diameter, as shows in as seen in figure here. So the standards are given by the ASTM, which is the American Society for Testing and Materials, specify the preparation of the test specimen, and which has a certain dimensions. The starting test specimen has an original length. For example, the starting specimen will have a original length L0 before the tensile testing. So, and it has an area A0. The length is measured as the distance between the gauge marks, just like I mentioned before. For example, if I have a gauge marks here and here, so these 2 points length is considered. Now, and again we measure the cross section of the specimen. During the testing of a metal, the specimen stretches and then next and finally fractures. So there are depending upon the type of material, the stress strain curve may vary. For example, for steel, it has a different stress strain curve. There is a locking and releasing of dislocation, or evenly entirely different stress strain diagram. But this is for normal metals, right? For example, if I take an aluminium, then it has this stress strain curve. So at first, the material will pass through the elastic region. In elastic region, there is only the elastic deformation. There is no plastic deformation. It's just the material expands, and once we release the stress, the material will get back to its original place. So, for example, if I take from 1 to 2, if I take y as 2, then the material has reached maximum elongation up to the elastic region. So if I release at this point the elastic limit, the material again regain its original shape, right? So once I pass it, we have an yield point. So where the material starts yielding, or the material, we have a plastic deformation which is going to take place. So again, to define plastic deformation, many people have defined different models, but the how the plastic deformation happens. Let's continue. So there are different models that define the plastic deformation. One was this model. There we have atoms, atomic planes. where we have atomic planes sliding on each other. So if I try to define a relationship, so because it is we are applying shear stress, tau will be force being applied T max sine 2 pi. We add one more slide. Sliding of atomic planes, then write it. Tau equals to tau max sine 2 pi. Suppose some atomic planes. They are sliding on each other. Let's say this is my length B and this is the lattice parameter is A. Then that will be equals to 2 pi x by so what is tau? Tau is shear stress, shear modulus times shear strain. So we know the shear strain equals to D by A. And if we take the small angular approximation, G times, so it is B by it is B by A times 2 pi. Cancel D for so it's not D by A. Then equals to tau max 2 pi x. Cancel GB equals to tau max 2 pi x. So tau max GB by 2 pi 2a. We take x equals to, then this is the GB by 2 pi. And this value is very much large compared to the experimental values. Why? Because the deformation, the nominant deformation mechanism is with the help of defects, and there are different types of defects. There are 0-dimensional defects, 1-dimensional defects, 2-dimensional and 3-dimensional defects. So for example, if we talk about 0-dimensional defects, we have vacancies, and we have Schottky defects, Frenkel defects, and we have interstitial defects, we have substitution defects. And if we are talking about the 1-dimensional defects, we have the line defects, which we call as the line defects. We have dislocations and also we have dislocations. So in this, if we talk about 2-dimensional defects, we have the free surface, the grain boundaries, the interfaces, the other faces. And for 3-dimension, we have the inclusions, we have precipitates, we have other phase formations, etc. And the dominant deformation, the dominant mechanism of deformation is through dislocation motion. So, yeah, next slide. So the dominant mechanism is for the deformation is because of the dislocation motion, right? So the dominant mechanism for the plastic deformation is the dislocation motion, and how this depends upon the size of the grain, which was given by the hull pitch correlation. For example, if I have a grain here, right? So if I take suppose if I have a grain and my dislocations are moving. Now let's first discuss how plastic deformation happens. So it's just like a worm moving. For example, these are atomic planes. And this is my dislocation core, and if I am applying stress like this, if I am applying shear stress, then this plane will start to move in this direction. So after the movement of dislocation, the extra half plane has moved some other place. Now what is happening here is the breaking of bonds along only one dimension is taking place, right? Only the one atomic plane of bonds are being broken, but not in place of this sliding mechanism. In sliding mechanism, all the bonds that are involved in both the planes, the above and below plane, is being broken. So there is involvement of a huge amount of energy, or a huge amount of stress that needs to be required for that model to be in par with this model, right? Or for the deformation. But in case of the dislocation motion, only the extra half plane bonds are being broken, or the planes that are surrounding the dislocation for like 3 to 4 atomic planes are being distorted. So that is the energy only required for the movement, for the formation of dislocation and the motion of dislocation, right? Now again, and this is the edge dislocation, right? So now there are two types of dislocation. One, we have an edge dislocation and screw dislocation. Now edge dislocation, if I have a Berger vector perpendicular to dislocation line, and in screw dislocation, the Berger vector is parallel to the dislocation. The dislocation line is nothing but the line defect, or the atoms where the line of atoms that are missing. That vector line is called as a dislocation line. And the Berger's vector is nothing but if I draw Berger's subcube, and the one unit vector that remains is called as a Berger vector. So we can even take the Berger vector, which is the same in direction of the motion of the dislocation line. So we can even define, or we can even think the Berger vector as that same. So the Berger vector and the motion of dislocation is always parallel in both screw and edge dislocation, but the only difference is the Berger vector is perpendicular to the dislocation line, but in screw dislocation, the Berger vector is parallel to the dislocation line. Now, let's say, now let's come to the Hall pitch correlation. suppose if I have a grain, now just like I mentioned before, the dominant deformation mechanism, there are different types of deformation mechanism. There is a film deformation, these other deformation is a tip deformation, that is, let's not discuss about that in this. Indeed, for the brief introduction, the intim deformation will have a twinning of planes rather than the movement of one atomic plane. There is the the movement of atomic planes in twin deformation. It is mostly possible in the hard materials like BCC and HCP materials, and even it is possible in HCC materials, but at very low temperatures or at cryogenic temperatures. Let's say we have a plastic deformation or the dislocation motion deformation. Then suppose if I have two grains, grain 1 and grain 2, and due to deformation there is a motion of dislocation, right? So once the dislocation comes across the grain boundary, it stops. Why it stops? Because there is in grain 1 and grain 2 we have different orientation of atoms, right? In grain 1 we have different there's orientation difference. For example, if in grain 1 we have 100 planes facing this direction, and in grain 2 we have 100 planes facing in another direction. So for the dislocation stops at the grain boundary, right? So for the dislocation to move from grain boundary 1 to grain boundary 2, so the grain boundary has to start deforming to accommodate or to move these dislocations from these grain boundaries. So we need a critical stress, right? Let's write that critical stress as S star. Critical stress or the critical critical shear stress or shear strain that is required to move the dislocations from grain to grain. And for example, in grain 1 we have n dislocations, and the total displacement will be given by NB, because each dislocation, for example, if each dislocation moves the top plane with respect to the top plane, the bottom plane will be moved by a Bezier vector B, right? If a dislocation moves from one point to another point, that is the total displacement that is given by the motion of or the displacement of a dislocation from one end to another end. That will be B. And if you have n dislocations, then we have displacement will be NB. And if we multiply the shear modulus, that will give me the force per unit length, right? And this is equal to tau minus tau naught times 1 minus mu, the Poisson's ratio, times by L, where my L is the length of the pylon. We know the shear modulus will be equal to, for metals is equals to 3 by 8, and also shear stress is equal to sigma by 2. Then tau minus tau naught will be equals to sigma minus sigma naught by 2. A few more slides. Substituting those terms, n will turn out to be sigma minus sigma naught by 2 times 1 minus mu times by L divided by 3b. L force 4 divided by D into sigma minus sigma naught D divided by strain, and this will be taken as a constant A. This A times sigma minus sigma naught strain to be times D. Now, for the moment of dislocation from one grain to another grain, this time shown here. For the moment of dislocation from one grain to another grain, so our shear stress should exceed the critical stress, right? So that relation will be for all the dislocations. If we combine all the dislocations, then that will turn out to be N T minus T naught times B should be greater than or equals to S star. And we know this is equal to A sigma minus sigma naught by D times strain into B dot sigma minus sigma naught by 2 times B should be greater than or equals to S star. Right? Then these two will multiply, they will turn out to sigma minus sigma naught by 2 whole square. So 2 doesn't come here. 2 will not come. Sigma square should be, let's write equal to, there will be no let's only take the equal piece. B star 2 times S star sigma B divided by A into 1 by D. Now we can write all this constant as a K. K equals to 2 times critical shear stress times strain by B divided by the constant A. And this sigma will be equals to sigma naught plus K into 1 by D whole power 1 by D. This relation is known as the Hall-Pitch correlation, and with decreasing the size of the grain, we can increase the yield strength of the material, but we can't just go on decreasing the yield strength of the material. Why? Because there is a certain limit. Once we reach below like 60-20 nanometers, once we reach the critical size of the grain, then again the yield strength will decrease now. See, if I draw that, okay, this is my yield strength and this is my grain size. It will go on increasing, and once I reach a critical size of the grain, this value will again decrease. For some materials this value will be constant, and for some materials this value will decrease. Why this happens? This happens because of the decrease in the grain size, and some grains will slide onto each other. When the material gets deformed, we will have a grain sliding, and because the grain size is getting decreased, there is a diffusion, there is a local creep happening. The grain boundaries. So there are different mechanisms that are dominating for the decreasing yield strength. So one is the grain sliding, right? So this is the Hall-Fish correlation. Now coming back to the tensile testing part. Yeah, the load and the change in length of the specimen are recorded as the testing proceeds to provide the data required to determine the stress-strain relationship. There are two different types of stress-strain relationship. Here, one we have engineering stress strain, and one you have true stress strain. The first is more important in design, and the later one is more important in manufacturing. So let's come into the engineering stress strain diagram. This part, this one is engineering stress strain, and this one is the true stress strain diagram. So in engineering stress strain, both the experiments are the same, but the data collected and plotted will be different. So in the engineering stress strain, we know the stress relation is load upon area, and this area for engineering stress strain is initial area, and for the true stress strain is sigma dash is load by the instantaneous area. Right? So the engineering stress strain in tensile test are defined related to the original area and length of the test specimen. These values in design, because the strains experienced by any component of the product will not significantly change its shape. The components are designed to withstand the anticipated stresses encountered in the surfaces. So a typical engineering stress strain curve from a tensile test of a metallic, for example, if we take a metallic specimen, will look like this. So we have an elastic region, we have a yield point which starts from where the plastic deformation begins, and then we have a maximum load, and this point is called as the UTS, ultimate tensile stress, and then we have another point which is called as a fracture, where the material breaks. I mentioned here at fracture we have a fracturing of material, or the material will fail, right? And the strain is given by the change in length, the original length, right? For the engineering strain, like change in length L, the instantaneous length minus the instantaneous length minus the original length divided by original length. This is for the engineering strain, right? Just like I mentioned before, the stress strain have two regions. One is the elastic region, and there is a plastic region. In the elastic region, the relationship between the stress and strain is linear, and the material exhibits elastic behavior where it tends towards original length, and this relationship is defined by the Hooke's law. The stress equals to elastic modulus times the strain. As the stress increases, some point in the linear relationship is finally reached at which the material begins to yield, and this point is called as a yield point. And the yield point marks the transition from elastic transition to the plastic region, and after applying a load, we keep on increasing. We have strain hardening of a material, because for a given strain we have to apply more stress, so there is a strain hardening of the material, and the maximum hardening can be reached at the ultimate tensile strain, which is called as UTS. After that, if we apply more amount of stress, the material breaks, and we finally have a fracture point, and ductility measures the fracture strain, right? So coming to engineering stress strain diagram, and for stress, for example, if I represent as a sigma dash, will be given by P by A, which is an instantaneous area, and the strain will be given by the total strain, engineering strain will be given by L0 to L dl by L. The instantaneous length will be equals to ln L by natural log of L by M naught. Right? So if I represent the the two strain and the engineering strain, so sigma equals to sigma dash will be equals to log of 1 plus the engineering strain. This is my relation. Now, so if my stress equals to Young's modulus time, if I have a constant slope, then the constant slope will be represented by Young's modulus times or the elastic modulus times the strain. If I am talking about the engineering stress time, that should be equals to engineering stress equals to elastic modulus time engineering strain or the strain. So this is known as the elastic region, and these will be shown by most of the ceramics, polymers, and this is shown by some of the metals. So up to this region we have it is a perfectly elastic material, and here we have a relation. There is a change of slope, and this can be related by K sigma n, and because and as n equals to 0, the stress equals to constant, and this defines the perfect plastic state. And for conventional materials, the n is greater than 1, so it looks like this. Right? The other testing is hardness. The other testing is the hardness testing. Moving on to the hardness testing, we have different types of hardness testing. One is a Brinell hardness test, and hardness tests are commonly used for assessing material properties because they are quick and convenient. However, a variety of testing methods are appropriate because of difference in hardness among different materials. For example, there is a huge variation in hardness when compared to the diamond and aluminum, the pure aluminum. The best known hardness tests are Brinell hardness test and Rockwell hardness test. So these two are the hardness tests that I am going to discuss here. The Brinell hardness test is widely used for the testing metals and non-metals of low to medium hardness. It is named after the Swedish engineer Brinell. So in this Brinell hardness, we have a sphere. First we have a material, and then we have a sphere indenter. In this test, a hardened steel ball of 10 mm diameter to 10 mm diameter to 15 mm diameter is used. So and the load can vary from 500 to 1500 to 3000 kgs. This is the load that can be varied, and the load is then divided into indentation area to the obtain our Brinell hardness number in equivalent to. So we have two terms. One is the diameter, one is the force or the load applied. The other term is the diameter of the ball or the indenter. The third term is the diameter of the indentation. So from these three terms, we obtain the Brinell hardness number of a material. So it is a function of the load. Write it as a P. My load is P. It is a function of my load, my diameter of the ball or the indenter, and the diameter of the indentation. Okay. So these are the three things. These the resulting VHM has a units of kg per mm square. So they are normally given in terms of a number. And coming to the Rockwell hardness test, this is another widely used test, again named after a scientist. In this Rockwell hardness test, a cone-shaped indenter or a small diameter ball with diameter of 1.5 to 3 mm is pressed onto the specimen using first a minor load of 10 kgs, thus seating the indenter in the. So for seating the material, we apply a minor load. So we get a certain position of the indenter into the material. Then a measure of 150 kgs or other value is applied, causing the indenter to penetrate into the specimen a certain distance beyond its initial position. The additional penetration distance D is converted into the Rockwell hardness reading. Right? So differences in load and indenter geometry provide various Rockwell scales for different materials. The most common scales are like a Rockwell hardness, Rockwell scale like A, B, C. Right? We have HRA, HRB, and HRC. And there are other hardness tests like Vickers hardness test, Noob hardness test, and also durometer, depending upon the material, depending upon the type of material and its hardness range. We use different types of hardness test. So that's all for today. If you have any doubts, please let me know in the chat section.